An overview, I have prepared slides of my research which will help us easily understand what actually crosstalk is and how we can reduce it in synthesized logics. Here is the abstract that in this paper we have discussed crosstalk noise reductions by several different methods. The important methods are gate sizing and transistor sizings. In gate sizing, it becomes complex for non-linear circuits, but transistor sizing also becomes complex, but transistor sizing is done by using graphical representations and heuristic algorithm, which makes it easy, and almost 50% of crosstalks is reduced using transistor gate sizing, so this method is most effective. Here is the introduction. What is crosstalk? Crosstalk is the impedance between signals that are proliferating on different lines in the framework. Crosstalk happens when two signal lines when the electromagnetic fields of two signal lines interact with each other, a noise generates due to disturbance of signals and signal lines, and hence crosstalk is produced. These crosstalk disturbs the incoming signals on the receiver, and hence the information gathered is not properly gathered, so it is important to reduce this crosstalk. Here are the methods of routing crosstalk reduction. Insertion buffer, gate sizing, and post layout transistor sizing are also used for crosstalk noise reduction. Development of an optimized algorithm is used for crosstalk noise reduction that give us room to explain solution space efficiently under delay constraint, and by using noise estimation method, we can also produce a crosstalk noise reduction method and TR sizing framework. All methods I mentioned above have limited effectiveness, so introduction of a new post-root gate sizing is used that help us to reduce crosstalk in highly complex circuits which are used in today's modern era. So as we go deep into noise reduction, digital noise is also becoming a benchmark, and due to this COSMOS and VLIC systems are designed. Our design flow is proposed for automatically synthesizing CMOS circuits that also help us to improve quality of noise effect. Here is the literature overview. The proposed techniques in this literature upgrades detailed rooted circuits, saving interconnects completely. The interconnected data expected for crosstalk commotion assessment can be totally acquired after detailed steering. The enhancement consequences of semiconductor measuring can be applied to the design totally on the grounds that the proposed technique uses the semiconductor measuring structure that can scale back the semiconductor inside cells saving interconnects. This structure is initially used. In this system, different driving strength cells are created on the fly as indicated by the enhancement result, and consequently transistor level streamlining can be executed in cell-based plans. Cell designs are produced by a design age framework called VARs. In this design framework, the complex circuit is divided into small segments, and each segment is tested individually that whether there is a crosstalk happening or not. If there is a crosstalk happening, that segment is corrected, and the corrected signals are transmitted to the other segment of the circuit, and there the signals are checked whether there is crosstalk voltage high or low, or is it negotiable, or it should be reduced. So as divide and conquer rule is used, similarly VARD is used. Similarly, the VARD format can be explained. VARDs depend on an embedded format strategy and is upgraded to deliver cell designs with variable driving strength. Taking advantages of this system, the proposed strategy diminishes crosstalk commotion productively after detailed steering. So as discussed, the entire circuit is divided into small segments. Each segment is tested individually, and after the detailed steering, the maximum amount of crosstalks are diagnosed and reduced. Due to crosstalk noise, nonlinear reliance on the connection post-root gate sizing for crosstalk noise reduction is a nonlinear optimization problem that depends on driver characteristics. In today's highly connected interconnects have a closed system size, making it impossible to solve the nonlinear optimization problem precisely. So in this study, we will use heuristic algorithm. A heuristic algorithm reduces the size of the aggressive drivers while increasing the size of victim drivers. So in heuristic algorithm, the aggressive driver, which means the transmitter, are reduced, which means all the transmitters are considered as one, and the victim drivers, which means the receiver ends, are divided into many parts. So that to verify that if the signal is transmitted to more than one channel, so whether the crosstalk reduction, whether there is crosstalk or not. So this makes the circuit more precise and enables the circuit for multiple connections of delivering a sound message. This duality is a crucial consideration in post-root gate sizing and must be taken into account to prevent the introduction of new noise violation while current faults. We approach the issue by providing a noise graph that is built using the design static noise analysis. All important nets, their significant aggressors, and the relationships between them in the noise graph are represented. In order to reduce system complexity, we create a sensitivity metric to remove weak dependencies from the noise graph. So after studying the circuits with different segments, our noise graph is made, which shows that where the crosstalk voltage is high or where is the crosstalk voltage low, where it is negotiable. So after studying the graph, it becomes easy to devise a solution. A cyclic sensitivity metric is used to analyze the significant cyclic dependence in the noise graph. Although high sensitivity cycles are removed from the graph by deleting a minimal number of vertices, cycles that are likely to converge are permitted to stay in the graph. So the circuits that likely converge the noise, which means that where there is more indulgence of crosstalks sound waves, so those vertices are considered in a graph, and minimum crosstalk sound waves are neglected. To create an acyclic graph, some edges from the low sensitivity cycles are momentarily eliminated. The next step is to sort the resultant acyclic graph topologically, where the topology of the noise graph stands in for the noise dependence links. After that, gate sizing is iterated. Digital noise is also becoming a benchmark as we go deeper into crosstalk noise reduction, and as a result, CMOS and VLIC systems are created. For automatically generating CMOS circuits, a design procedure is put forth and also aids in enhancing the quality of the noise effect. So here's the methodology, how heuristic algorithm works. We go through our noise estimate technique based on a superposition that takes temporal window into account for a net with numerous aggressors. So here in the figure we can see that there are number of aggressors, the receiver ends or the points where their crosstalk happens. Closed form noise waveform noise estimation for two partially connected intersects. Noise from each aggressor are superimposed by more aggressors. Multiple sinks becomes interconnects that are only partially linked. So after that, crosstalks are measured at each victims and then calculated in the form of graph. Here there is the noise form equation which is derived while considering the elements that are used in a circuit. Here is the overall optimization algorithm. So in this step, we first figure out crosstalk noise at each circuit net. Then we find the circuit's maximum crosstalk noise voltage. After that, the maximum voltage of crosstalk and the threshold frequencies are considered. Stage 3 is to select the network in the list L0 that has the highest noise voltage and carry out optimization as described. The optimization's target value is the value of Vmax threshold. Update the time window information and remove the net from the list L0. Stage 4 is the complete the optimization process. If the L0 becomes empty, then repeat to the stage 3. Here is the noise graph representation. The way how our noise graph is represented. A noise graph G with V, A and E has edges E and vertices vertices. In the noise graph, vertices stand in for nets. Vertices come in two varieties. Nets that have failed or are on the verge of failing the noise analysis are represented by type V vertices. In other words, the type V vertices will present in nets with noise slack lower than a predetermined positive value. Drivers with vertices of type V are suitable for sizing up. Vertices of type A represent significant aggressors with minimal noise. An aggressor who makes up at least 20% of the overall noise on a victim net is considered as a significant aggressor. The network with very little noise has more noise slack than previously measured positive slack. So here is the way how our algorithm is sized. The pseudocode of the proposed algorithm is shown below. At input, noise analysis results output. So at the output and instance cell is replaced by directive begins. So here are the steps of how an heuristic algorithm is designed for crosstalk noise reduction. Step 1 is to construct a noise graph. G is equal to with vertices V, A and E based on noise analysis. Step 2 is size down type A vertices on the noise graph. Step 3 is to analyze the cycles where there is more crosstalk and where there is negligible. Step 4 is to break the cycles of noise crosstalk noises. Step 5 is the topologic sort, and step 6 is the repeats until there are convergence. Step 7 is for each vertex in GS repeat the previous steps, and at the end size up. And crosstalk mitigation techniques: minimum width among traces, keep traces on adjacent layers perpendicular, use ground planes, exploit ground return path, use differential signals, reduce the width of parallel traces, isolate high frequency signals from other traces. So this was the way how crosstalk are reduced in digital circuits using transistor gate sizing methods. A small summary is: first, each crosstalk voltage is recognized at each segment of the circuit. Then a graph is plotted where there is more convergence. That convergence is reduced by adding suitable transistors gate sizings and logical gates, which repels the crosstalk noise and allows the sound signals or any kind of data signals to flow through the transmission lines to the receiver without any interpretations. So the conclusion of all this gate sizing and crosstalk reduction is that crosstalk noise reduction by transistor size can reduce the maximum noise voltage by more than 50% without delay in